would like to introduce to you the IEEE Consumer Technology Society, and the agenda for today is we will go over the Consumer Technology Society introduction with yours truly as a chair. Then we'll be presenting by Jill and Basal from Intel, and I would like to extend my thank you. And then we'll have 15 minutes for the networking. And if we go plus minus 5, it should be okay. So during today's meetings, please post the pictures, tweet, share, do anything you feel like. The more the merrier. This is the chairs and volunteers for this year, with Deb as the co-chair, Avid as the vice chair, Pat as the secretary and treasurer, Joseph as the marketing chair, Michael Wong as the program chair, and Joseph as our webmaster and jack of all trades. We're looking for additional volunteers and speakers. So if you know someone who would like to speak or volunteer, please send it over. The next two meetings which we will have will be on March 25th from 12 to 1. This will be on medical devices by Eurodeaf and IntelliFlow for people with disabilities, delivered by Derek Herrera. And Derek is a U.S. Marine veteran. He was a Marine SEAL, and then he went to UCLA Anderson. And lately he became an entrepreneur, and he's working with a number of the authorities and government veteran hospitals. He actually was the first one who was wearing the exoskeleton from Israel in U.S. He was ringing the bell on the NASDAQ, so it's going to be interesting. And the one after is on April 14th, is the RISC-V and Consumer Technology delivered with Ted Marina from Western Digital. So it's a RISC-V Foundation, which will be talking about what the RISC-V is doing and the new trends. I will skip the poll for today, but I would like to encourage you to become a member of Consumer Electronics. We have a great promotion. We have also the marketing campaign going, so anyone who can recommend the professional gets a $15 off, and anyone who recruits any membership gets $5 off. You will receive the magazines, you will receive the different types of communications you can publish there. The topics and suggestions, please send it over. We also would like to see if anyone has any job opportunities or looking for people. You can send us an information and we will share it through our distribution list. Same comes with the job seekers. And for today, I'd like to do the speaker introduction. Allow me, it's my pleasure and honor to introduce Jill Boyce. She's the Chief Media Architect at Intel. Jill is Intel Fellow and responsible for defining media architecture for Intel's video hardware designs. She represents Intel at a joint collaborative team on video coding and video exploitation of ITU Alliance and the Alliance for Open Media. She serves as an associate reporter on ITU VCEG study group of 16. She's an editor of Versatile Supplemental Enhancement Information, companion spec to VVC, and editor for the MPEG-I Immersive Video Draft Standards, and was an editor of Scalability High Efficiency Video Coding Extensions. She's the director of Media Coding Industry Forum and serves as the Media Coding Industry Forum Work Chair. She's named of IEEE Fellow in 2019 for her contributions to video coding. That's a full mouth, Jill. That's a lot of work.
Sure.
Wow. And Basal is an immersive media algorithms and standards architect at Intel and responsible for delivering media immersive experiences on Intel devices. He has a PhD in electrical and computer engineering, MS in optical science at University of Arizona, and electrical engineering from University of Oklahoma, BS in communications and engineering from Aleppo, Syria. His research interests are light sails, point clouds, mixed reality, immersive video systems. Basal also serves as an editor to developer of test model for MPEG immersive video, and he has more than 35 published papers and patents and many contributions to the MPEG standards. And the topic of today's discussion, after such a great honor, is immersive media enables viewers to experience interactive content in 6 degrees of freedom from any position and orientation within a supported viewing space. It enables experience requires significant data and computer resources, which makes it an interesting challenge to Intel to solve. So the upcoming MPEG immersive video standard will enable compression and delivery of immersive media content to end devices. Intel leverages the video codecs, graphic capabilities, and its upcoming discrete GPUs to enable immersive visual experience that responds to interactively end user motions. We will describe the media capabilities in Intel Xe GPU architecture, highlight the importance of immersive media, and MIV operating model. So, and then hopefully we'll see the media immersive demo. And on that note, I would like to pass the floor to Jill and Basal. Thank you very much.
Thank you, Olga. Basal, why don't you go ahead and share the screen? So thanks for having us here virtually today. So I'm going to start out and talk a little bit about Intel GPUs, and then hand over to Basal, who's going to talk more about this MPEG immersive video standard. So Basal and I are both part of the group in Intel that builds media hardware. So it's the video encoding, decoding, processing capabilities that goes inside of the Intel GPU. And where the immersive video is one of those applications where we're just trying to have new exciting use cases that make people want to go out and buy the latest, greatest PC that has those capabilities. So Intel actually has a long history of building graphics hardware, which includes this media or video capability. Early on, it was discrete, and then it became a chipset, and then for a number of generations, it's been integrated within the same chip as with the CPU. But recently, we've announced this new Xe graphics architecture, which can be used for both integrated and discrete graphics. And so every kind of generation, year over year, we have new features and improvements in capabilities. And so there's been announcements made of 3 different products so far that are based on the same architecture. So Tiger Lake, which is the newest CPU, and newest computers are actually available now. DG1 is a discrete graphics card, and then SG1 is being used for servers for on the visual cloud. So at a high level, the Intel architecture is so within the GPU, there's 3D capability, and then there's media, which is the video, and then memory fabric, and cache. And in our immersive video, we make use of both the GPU, the graphics, the 3D portion, as well as the media portion. Go to the next. Within the media, so we're in the group that's the media group that works on the video capabilities. So we have, there's multiple different fixed function units. And there's been a trend of late to have fixed function media rather than just using the GPU, so that you can have improved performance and power and reduced area by having dedicated hardware for specific video capability. So we have the ability to do encoding and decoding and transcoding of multiple different codecs. scaling, and then some video enhancements. Go ahead to the next. So some of the newer features in the latest version are improvement in throughput, addition of new codecs like AV1 and features like HEVC screen content coding, higher quality, higher speed playback, and Dolby Vision playback. Go to the next. And then Intel actually has a one API software architecture that allows developers to have this interface to the accelerators, including the media hardware through the one VPL. So these capabilities in the Intel media and graphics is being used then for our immersive media. Go ahead next, Basel, and you can take over.
Okay, so thank you, Jill. So as you see, that was a quick background on the Intel GPUs used. And I'd just like to switch a little bit gears. So let's talk about like the immersive side, and then both aspects will be merged when we're talking about the demo. So with this one, let me start first introducing what we mean by the immersive experience. It is an illusory environment, completely surrounds you as if you feel you're part of it. You might be able to interact with objects in that scene. It's typically captured from through multiple camera arrays, multiple cameras like for moving or static objects, whether real or virtual. And the point is like you can encode and deliver and decode such that the end users can navigate the content from any position, angle, or any moment in time. So what we're basically like meaning here with the immersive media, you are having like the 6 degrees of freedom. So basically 2 main characteristics, like you have the support of the wide field of view. So I can rotate my head in all different directions and still be able to get the right content. And you also have the motion parallax. Motion parallax, like as you are translating in your position, so you see the relative motion between different objects in the scene. And this is really a very important depth cues because this is deliver a more natural way for people to consume the content. So this will really take the experience to a whole new level. So immersive media does deliver this 6 degrees of freedom. And one of the cool things about it is it can be consumed on a wide range of devices. Like, so those are already accessible by millions of customers. And that's also make it like very interesting. So typically people would think like maybe it is more like when you say immersive media, they think directly like head-mounted displays, like VR, AR experiences. But head-mounted displays are just like one platform. You can consume that also on regular like screens with built-in camera and laptops. In fact, the demo I'm going to show you today, so it's in that targeting that platform. But you can also play it like on smartphones, tablets with their inertia sensors to capture the motion. Or you can have like the more high-end like displays, like regular volumetric displays or light field integral displays. So as you have the capabilities to render like whether the volumetric content or like different views and retarget that for the end users. So it's really immersive media can scale. So that is from the display side. If we look from the capture side, you can capture from a variety of devices, right? So you can have, like, for instance, a pure planar camera array. You have many cameras like in the same plane capturing the content in front. Or you might have like cameras like pointing inward. So like capturing the objects from different angles. And then people may be able to walk around and see through that object. Or you can have like cameras pointing outward, like as you can see here, like for instance, like Facebook or Google jump rigs. And those might be like multiple cameras, but you can also have like there's this category of light field cameras that's like light or ray tricks, although they are delivering like multiple views, but within like certain baselines. So you might need some kind of like processing in order to amplify that baseline. So immersive media can really target a lot of many applications and deliver a really improved experiences. Like among those, like for instance, like the e-learning. Now, everyone here, we're living in this COVID era, and people has to study like remotely, or students. So here you can really have like these objects, whether like science or health in this case, like so, and be able to really look around from different angles to comprehend more. Immersive sports, and there's already like deployment from that, like Intel Sports, like deploying a lot of cameras in the arena. For those, like you might have it like some immersive meeting applications. You can improve like streaming services, live events, or do it yourself like instructional videos. Like if you want to really let people see like certain process or kind of like experimenting like descriptions of a prototype from different angles. So with that, now we understand immersive media, but let's now zoom into the problem at hand. So when we say immersive media, it's typically requires a lot of data, compute, and bandwidth, and those are make it like really challenging problem, and that's why Intel is interested to work on it. Currently, like the current situation, like this kind of like 6DoF capabilities are limited to the capture side. Basically, you might have like the multiple cameras and servers, like maybe next to the events or arena, or maybe somewhere like close cloud. You might have like the director sitting there, and he's like dictating like where's the navigation path of the virtual camera should be. And then so you end up having like synthesized a 2D view from that virtual camera. And this is what really like you send it to the end user. So end users don't have any video freedom. They just consume regular video in this case. Obviously, the infrastructure is not ready yet. And that's why like you really need to have a compression protocol in place in order to encode, decode, render this kind of content while not harming like the ability to render 6DoF at the client side. So with that in place, I'm going now to talk about like the MPEG immersive video. Let's first like the high level of all MPEG immersive standards. Of course, MPEG is one of the standardization bodies. There's also other standardization bodies actively working on the solving the same problem. But within MPEG, there's this larger umbrella, which is MPEG immersive, and among it, like there's the kind of like V3C or VPCC point cloud, let's say like efforts. And this is already finalized and already available like in the first version. There's an extension to that, like related like to how to do like mesh processing for the V3C. And you also have the MIV, which stands for MPEG Immersive Video, and that's like I'll be focusing more on that in this description. Obviously, and yeah, we can talk more about it, but basically, like the main differences between the point cloud and the MIV is obviously like VPCC takes like point clouds as an input, so you have like RGB and position of each point in the scene, and you start to processing from that, while MIV is taking the multiple video streams, like capturing like from regular cameras directly and process those. So MIV is already like in community past the community drafts. Now it is moving to the kind of like the final stages in the standardization, and it is aiming like to be like mid 2021 or October 2021 to be finalized. So besides that, there's also like some kind of like efforts to do a geometric point cloud compression, like something like more suitable for autonomous driving and drones, and something like sparse representation of content. So if people are interested like in point cloud, this is like a quick description here. So you typically start from a point cloud and you project it like to a surrounding cube. And then you have like all these like 6 phases of the cube projections. Then you are extracting these and packing them like in something called atlases. you do the same operation for both the texture and the geometry. And then so you can do like some kind of padding to make it like more friendlier to the video codec, more continuous. You run the regular like video coding on top of that. So those are both MIV and VPC agnostic to the what kind of like video coding you can apply. And also, of course, you will be having metadata which tells you how these are mapped to the original content. You do the processing, video decode, and then do the 3D rendering. So that's just like quick. For MPEG immersive video here, which would be based here, it says industrial effort aiming for providing data access. It's based on this like the kind of like the parent standard, which is the visual volumetric video-based coding, or what's also known as V3C. It takes this input of multiple views, like whether like the texture information, the geometry, and camera parameters. Do the encoding. So in order to extract only the meaningful information and throw the redundant parts out, pack them everything in atlases, do the encoding, and then from the decoding side, you reverse the process. And for the rendering, you are doing it interactively based on the viewer positions. So that's position and orientation. So you have the right perspective rendered to you kind of in responsive manner. Again, the MIV is it's obviously like you can be using it with any video codec, like whether HEVC screen content coding, AV1, VVC, AVC, you name it. So, and there's nothing prevent that. But point to mention that there's high-level syntax to indicate like alignment of atlases in the views, like how to enable like view-dependent streaming, substream access and decoding. So there are more details to that, like already supported in the standard. In terms of like the content here, so you have a variety of test contents we are testing MIV with, and those can be like with a linear camera arrangement, a planar camera, something like outward-looking camera, inward-looking, or even like spherical. So you can see it can really goes cover a lot of different variety of content, and this is also it's not only like it can support both like example as you see here, both natural and synthetic content. It can support like whether perspective projection or equirectangular projection. So really there are plenty of formats through that. And then basically as like the operations here, like in MIV typically we start with the cis subset of the or the set of views available to you, whether the texture information and the depth. And of course, like if you cannot capture the depth directly, so you can estimate it from the texture itself. And then you have the camera parameters, so you know the position and orientation of each capturing camera as part of the calibration process. So those are the inputs. The first step is really to do like view selection. So identify like maybe a few views here like to be like basic views, meaning like those will be sent as is. The other ones would be additional views. That's mean like those are the ones to be pruned, and only the meaningful information will be kept. In this case, like so you can see with the pruning step, so you have only the occluded regions, something that missing, not available in this like other basic views or previously pruned ones, or maybe the edge regions, and those are the ones that propagated. There's a step afterward, like to do the extract the patches, and patch is just like rectangular area. So you extract all these like nearby like pixels together and pack them in a more compact manner in something we call atlases. So you can see this kind of atlas has like these like the full views, and also like have these like small patches coming from all occluded regions from across all other views there. And of course, you can do the same operation for both the texture and the geometry, and you can send them at different resolutions for if you want. You do then the regular encoding. You have the metadata also encoding process, multiplex everything in a single stream, send, demux, decode, and then do the rendering. And this rendering happen interactively with the viewer position and orientation. So I can take questions here if people have something about the MIV operation. Yeah, if not, I'm keep going.
I unmuted everyone, so you guys can ask questions, or I have one question ready.
Yeah.
Okay, let me ask it. The question is, will Intel be planning to support low power ARM-based implementation on MIV?
Let me get back to this question like by the end of the demo, because that would show like explain more on that. Yeah. Okay.
Okay, then let's keep going.
Cool. Thank you, Olga. So just like one of the other MIV modes, like it's the MIV view mode. So MIV view here, like it's you have subset of views available as well. So it's very similar to the MIV mode, but instead of really doing kind of like this kind of complex operations, so you can select subset of the views, pack them in certain manner, encode, decode, and stuff. So the only thing different is just like rather than doing this kind of like pruning and this packing of like very tiny patches, you just pack like larger patches, which represent like views in this case. So this would make it like for some certain like operations like fast kind of like real-time encoding, less wait like and do like fast decoding. So this might be more practical, but at the same time, it's not maybe the most efficient way, like in terms of bandwidth. So, but this is like this kind of like different operation modes that is supported. So, in addition to this MIV Atlas, which is the this like regular patches or the MIV view, as I showed, like so subset of views, you have like something called like MIV geometry upsend. Which is basically you don't even need to have the depth maps available to you, so you can just send like subset of the views directly, and you can maybe depending on the rendering algorithm, if it's need depth, you can estimate it like at the decoder side, or you can just process maybe without the need of that. And there's also the MIV entity, which is the capability even to extract objects inside the scene, like on object by object basis, and stream them. So, for instance, you might be caring about like only sending the foreground objects and discard like the background. So that would give you like significant improvement on the in terms of bandwidth. So, okay.
There is one question. Hold on just 1 second. There is a question from Patrick. Does the viewer need a special tool to convert basic view to a pruned view?
So it is basic, no, like the thing that is being used is just projection. So it's very typical. You unprojected to the 3D coordinate, reprojected to that view, and then take the subtraction. So you figure out only the occluded regions and pass it there. So those are like very typical operations that you use. So you don't need something like special.
But the one thing I'll mention again is that this is the encoder side operation. Right. So the viewer, doesn't have to do anything special. It's just going to decode what was sent to it.
Yeah.
Thank you.
So I just want to highlight one special feature, like in also MIV supported. So it's you can do frame packing, which means I can have like multiple textures, content like packed together, like from the same component with all like textures, or also across different components like textures, depth maps, or even occupancies. Occupancies are just like will tell you like the if a certain pixel is active or not, like within the patch. So it's just like very binary representation. So you can do that like for different kind of formats. And actually, the demo I'm going to show you later on, so it is using like making use of this both the MIV view approach and also the frame packing to make everything like in single video frame. So with that, we're getting close here. What we did here, it's as an effort to really simplify the process to get really MIV deployed at larger scale and use like a lot of already established infrastructure. So instead of so we had interested in putting everything in a single video layer, and obviously the reason for that those are widely optimized in the media hardware like of GPUs on, and you also have like a lot of like video players supporting them. So that will simplify the process. And also you don't need to worry about like the synchronization and buffering issues, right? Because as long as you're packing all these video elements inside a single stream, then things really should work like as in the most simplest way. And the key idea here, like all this metadata information, which tells you, like, for instance, the camera parameters, how exactly these patches in the atlases are mapped between the atlases and the views. There might be some information about like the depth ranges and stuff. So all of this, rather than sending them like in separate like units, so we are actually adding all of these like in a single SCI. So just like packing this in a single SCI, and you can inject it directly in a regular, in this case, like HEVC bit stream. So it will be handled as any regular HEVC bit streams without any change. But you will have this additional SCI which tells you this added information, and using these information, so you can make sense of the decoded content in order to deliver the right immersive experience. So those are kind of like the changes here. And one of the key things as well, like we already tested this approach. So it does work with legacy streaming servers. Like you don't need to change anything from the streaming side or server sides. You just need to do like some modifications on the decoder side in order to really get this immersive experience. Okay, so and this is like, this concept is actually what we use like in our demo, and this is, we're calling it like Freeport Player. It says to show like immersive video playback on Intel GPUs. In this case, we're using like XE Max, or what's also known as DG1. So as you know, like the GPU itself will have both the media and the graphics. So we are using both sides really to deliver, because immersive media, you need both aspects. So it's unlike like other maybe applications. The media part, like you have a dedicated fixed functions that can process like at low power, high performance operations. And then you have the graphics aspects, which really a lot of like rendering processes like can happen there, and still deliver a very good quality with a good performance. So with that, so we're going now to the actual demo here. So the Freeport Player, it's actually it's built on multiple components here. So one of the first components we're using is just like the open source like VLC player. So we just made sure like this can run with typical frameworks. And one of the advantages also with the VLC player, you basically like you use like a lot of already built functionalities, like delivering the frames at the display order. You can do the pausing, rewinding, looping. So a lot of these things. So you already get it like for free when you bundle with these players. And what we added on top of that one, so we developed a special video filter that is like, once you select it, so then it will trigger this immersive mode, and this filter will now make sense, like extract this MIV SCI information that we are embedding inside that HEVC bit streams, and making the renderer acting on based on that in order to really deliver the right content. So those are the kind of like modifications we did, and it's really, everything is fully integrated with that VLC. And most important, both the decoding and rendering operations are happening on using the hardware blocks, like so on Intel DG1 in this case. And this is the rendering stages like are done, implemented using the DirectX 11 shaders. So everything is multi-threaded and run like very efficiently. In addition to that, so we have this kind of like face tracking support. So we have this kind of like pre-trained OpenCV neural network module, and we did some kind of refinements to denoise that content. But as the viewer is moving around, so you can get like really that content rendered the right way. So let's take a look at the bit streams actually we use like for the, I'm going to show you the demo based on. So we use like, for instance, like I'm going to show you two sequences. The first one is the frog, which is like just like linear array of views, and you will have them in this case like 13 cameras, but I'm just using like maybe a subset of these views, like 5 views in this case. Put all these textures informations on top of each other, and then pack the geometry, and geometry is downscaled by 2x. We pack them in more compact manner, so We don't use waste a lot of pixel rate. And we do the same thing like for Painter. Painter is 4x4 camera array sequence, so we selected the 4 corner ones plus 1 from the center. This entire sizes is about 1280 720 resolution each view, and then so the total would be about 1280 by 4680, and this is running at 30 FPS. And of course, you have, as part of the bit streams, you have actually the MIV SCI information, which tells you all the information you need to run it. If you try to run it, this will be just single stream. But if you try to run it and decode it on regular, let's say VLC players or stuff, so it will just decode the content as it will decode any regular HEVC content, right? So in this case, it will just show you you have this multiple views and decoded atlases, but it does not act further than that, unless you have this video filter selected. So this is both for whether you have for the Painter sequence or for the Frog sequence. It's the same manner in this case. But if you have acting that filter selected, then I basically can run the demo now. And this one here, it is pre-recorded, so but I'm going to speak to it live, just to walk you through this. So this is the Frog sequence. Run it through the Freeport player, so you can see me here live at the when recording the demo for sure. So this is me moving around from left to right or right to left, and you can see the scene is being rendered according to my position, which is very cool, and really you can make sense more with that content, as if this is something really in front of you. And make sure something to mention we get the right occlusion relationships, and it's not only we can move from left to right, but we can also zoom in and zoom out. And if I can go extreme to really most to the right or most to the left, so you can see more of these imprinted regions, because obviously you don't have a lot of information there. One of the cool things with this player, I can pause, and then I can really look around to see what's happening there. So you can see all these occlusions and the right relationships between the different objects. And this is kind of the time bullet effect. This is something really valuable, and you get it with this immersive media thing. So you can choose to pause it. You can rewind to previous moment in time, replay again as you're dealing with any regular video players. And still go around, and you can see that content being really rendered the right way. So you have this kind of motion parallax support, and I can move even if this is just linear content, I can move vertically, go up and down and look, and you can see it will render the right content. Of course, you don't have that information, so you have these imprinted regions. Again, this is the step in and step out, and everything really responsive and I can move in this complex motion, doing everything there, and it is really it's behaving the right way, as it should, as in case you are part of that scene. So that's yeah, that's really cool things. Okay, so in addition, just to show you or prove this is running on the XE Max or Intel GPU. So I'm going to open here the task manager as I'm going. And let me, okay, so this one here, so you can see the GPU being used here is the Intel Iris Xe Max. So you can see both the 3D engine, the video decoding part, for instance, and the memory utilization of that one. This is all happening in very responsive manner, and you can see all this kind of 6DoF effects delivered. So you have again, it's real time. It's very responsive decoding and rendering. So everything happening on the Intel GPU. Okay. So the other demo I'm going to show is for the other sequence, which is the Painter in this case. so this is again it's captured from 4x4 camera rig. So here's me again. As you see me like start to move left to right, so you can start to see this kind of like motion parallax effect for different objects in the scene. I can move also up and down, and you can see more kind of the content because this is like a 2D rig system. So you have more of this information. If you go more to the extreme, so you can see more of the impacted regions. But this kind of like motion parallax is really powerful when it is in front of you. So other than the impacted regions, of course, like you might see like some little artifacts around the object. Those are coming basically from the depth maps that we are also working on improving. Same thing here, you can pause and you can go around to really see what's happening. For instance, you can see the table, the books on the table versus the background. It's really rendering the right things. It's not hallucinating something weird, but just as if like you are really there. And then so you can rewind, you can replay again. Besides here, you can also like do kind of like step in, step out. Besides the motion, so you can see me also moving closely to the drawing, for instance, or moving to the book, for instance. Like so, you get closer to that, and then I can step back again. So you can see like everything like the field of view being changed the right manner. So this is really cool. And you have this 6DoF delivered with the time bullet again. So that gives you really the all in action. So yeah. By the way, this takes like the video consumption experience to a whole new level, because really instead of just dealing with it as fixed from fixed perspective, now you can control and you can decide like where you want to look at that content. This is again the complex motion, so you can move like in any directions, and it is just tracking me always and responsive to that. This is again showing the task manager just to prove this is being run on Intel GPU Xe Max. So you can see again the 3D engine decoding and memory utilization of the DG1 system. So we have a 4 gig dedicated on the Xe Max card, and remember here we are decoding and rendering from 5 views at the same time. So all of them are being used in very responsive operations.
There was a question here that says about what is causing the artifacts on the background.
Right. So it is so 2 types of artifacts. Like if you are if you are going like beyond like certain range, for instance here. So this is, you don't have this information from the capturing system itself, so it will try to impede some of this information, for instance. And there's like these around like the edges, like those are remember this is like real world content, so it's hard to get down to depth map. So this depth estimation algorithm, as you keep improving that, then you should be having like a better content there. Okay. So I hope you like it. If we go quickly back, because I want also to keep some time for the discussions. So free player, the one that you saw the demo, we're really making use of most aspects like on the GPU. So there are some like light operations happening on the CPU, which is dealt with input-output operations, like the metadata extractions, parsing. Those are very lightweight. The face tracking operations, like with the camera. And this is, by the way, just regular like built-in camera, right? So or cheap webcam, so you can get it running on your side. The most important, the decoding part here is happening on the media part of the GPU. So you also have the format conversion, the buffering operations. It's all dealt on the media part. And then there's this green part which is running on the graphics aspect of it. So here's showing a lot of like processing stages for that rendering, and then everything being also again sent to the display part of the GPU to show it like directly display from that content. So we try to minimize like the data transfer between the CPU and GPU, and keep everything like lightweight and responsive there. And this is just a quick explanation, like for some operations happening on the rendering side. For instance, like we're taking this, we have this input like video stream, and the first thing we do unpacking, so we get back like the regular atlases as we generate like from the encoding side, and we do upscaling for the geometry to get back to the nominal resolution. And then so there's some parts like where we reconstruct the occupancy, figure out where exactly the active pixels, and actually we do also a patch culling, so figure out what are the regions in the images actually contribute to the final target viewport. So if some regions are not contributing, then there's no need to process. You can truncate them away. And then there's this process, like you're taking them from this atlas representation and show them like in kind of like a view representation. So this is the prone view reconstruction, where you actually see the views and you see the kind of like truncated regions from the regions that's not contributing to the final viewport. You do then this kind of like unprojection, reprojection to the desired target image interactively. Of course, you know the targeted viewport information, so you know how exactly to project. And then, so as part of the projection, so you'll be having these depth maps now will be aligned. Remember, like when we start from the input source, like those are in the view space, but then when you send them to the target view space, then everything here will be all aligned. You will be having some gaps in some views and some complete in others, depending on the position of these cameras. Then depending also on the weights, like how close these cameras from the viewport, we can also blend and merge all of these together in a single final depth map. And there's also some tilting operations on top. And then you do the same for the texture. So this is how you get the final synthesized viewport. You might have like some kind of like regions like remain like as a wholes. For instance, you can see here these like kind of cyan regions, and then you can run the inpainting in order to fill them. So the inpainting, by the way, it says currently implemented is very simple, trivial one, so just like nearest interpolation. So it's not the best way, of course, like, and that might be also producing some artifacts that maybe answering the questions, one of the questions here. But this is just high level of the really GPU implementation of that rendering. Everything is, remember again, like it's in shader language, it's multi-threaded, and run in a very responsive manner. Just to conclude, so immersive media gives a more natural way to consume the content. So we really think like this is we take the experience to a whole new level. The immersive ecosystem is emerging. Now we have a compression or streaming protocols being developed and will be soon available. For instance, MIV, like something coming like within the next like 6 months. Freeport Player is a proof of concept, like you can interact and navigate that immersive content in a single video stream in a very simplified manner. So this is very simple implementation of MIV using the SCI approach. And we know as we're working like on the playback side, but we know that the content creation is another key piece, and you need really to develop the full pipeline and really to deliver the right usages to the end users. Like so, content creation. So meaning like we need also like from dealing from multiple camera captures, like the depth estimation, which is a work in progress. What you saw, the demo is running on XE Max GPU. And remember, this is an entry level. This is just like a lightweight. It's not yet like it has the full power, let's say like for graphics part, but it is capable of handling immersive workloads. And that's really promising that this is like entry level. Then we're really excited on what Intel can deliver later on. In terms of GPUs. So with that, this concludes my our talk, and then we can have more questions here.
Okay, thank you.
Sure.
So I have a couple of questions
Go
right
ahead.
now. So the question number one, which did anyone answer that? What is causing the artifacts in the background?
Yeah, so this is, as mentioned, like there's some impacted regions if you move beyond the background, the capturing system itself. Like you don't have this information, so you try to implement that. There's parts like coming from the depth map itself, like around the edges, that also can be improved when you improve the depth maps. It's also, remember, like real world content, it's always challenging. If you have like synthetic content, of course, you'll see a lot of these things are gone. So. Of course, there's some also maybe some details in the implementation that we're also improving.
Yeah. There was a question for Jill. Intel encoder has always only support for 4:2 ratio. Is the new GPU support 4:2 ratio or 4:4 ratio?
Sorry, repeat. Sorry, say the beginning of the question again.
Let me copy paste. Well, I cannot. It's in the chat. So Intel encoder has always only support 4:2 ratio.
420. Okay, yeah, okay.
Is the new GPU support 4:2 ratio or 4:4 ratio?
I'm trying to remember when is the rollout. 422 and 444 support, I believe, is present inside the new Tiger Lake GPUs that are out.
Thank you. And another one is this list of questions, which maybe some of it was answered, but I'll just reiterate it. Will Intel be planning to support low power or ARM-based implementation on MIV?
Well, ARM, I mean, where Intel is adding support on our platforms, right? So we're not going to be adding support for someone else's platform from Intel. However, MIV is a standard, right? It's an industry, will be an industry standard, and so any companies that want to are able to build implementations for the standard.
Yeah.
And
just
how much
like,
of MIV will require? Go ahead.
Just to mention, so I think the second part you have in that question, so low power GPU. So DG1 or XE Max, this is already low power GPU. So, and this is like meant also like to be integrated on laptops, and this is what we did the demo on. So right, so meaning like it definitely can work on these low power GPUs.
Yeah. And how much of MIV will require or use embedded hardware blocks?
So that part again, how much will, just repeat the question?
How much of MIV will require or use embedded hardware blocks?
Dedicated hardware blocks. So we have the hardware video encoders and decoders, and we have the GPU. So those are the key pieces of hardware that are getting heavy usage in the MIV implementation. There's also some software layer above that, but the most compute intensive portions are done by this fixed function media hardware, encoders and decoders, and then on the 3D graphics, the GPU.
Right.
Thank you. Next question, will Intel be implementing MIV by combining the encoder and decoder function in the same block? So standard cameras and displays can be used as a source and display ends.
I think
I will repeat it. Will Intel be implementing MIV by combining encoder and decoder functions in the same block? So standard cameras and displays can be used at the source and display ends.
So encoder and decoder will be separate. They're not combined. I mean, you might have content creation being done one place and then playback on another. On the playback, which Basal has shown on that demo, I mean, we're using an existing display, right? Mm-hmm. And so we've chosen to implement this decoder player as a filter for the VLC open source video player. And so the actual display connection, the video decoder that already exists, the hardware video decoder can be used and the software can be used in the existing display by adding this additional filter to do the view synthesis operation.
Yeah.
But the encoder decoder won't themselves be combined.
I just want to maybe add one thing. So the demo I just showed was using a one video decode box. So the DG1 actually comes with 2 video decode boxes. Like, so we did not even need to use the second one. So you can add, it's so powerful that in terms of like encoding and decoding operations, such that like you can really have like even more views and even larger video frames, and can still like keep up and deliver like in real time. So
Right. Any other questions? I muted everyone, so you can unmute your microphones and ask questions, audience. Okay. We are reaching up to the hour, so I'd like to thank Jill and Basal, and I will formally close the IEEE. And I just want to give a minute to Tom Coughlin, who introduced us to Jill and Basal, and I want to thank you to Tom for doing that. Tom, if you want to speak after we concluded our IEEE session.
Oh, so I think Olga's, hi there, can you hear me?
yes.
Oh,
Yes.
so I think Olga just wanted me to let people know that I have a petition to run as IEEE president-elect. There are 3 candidates right now for president-elect, and I have a petition to run. And the petition is located at www.ieee.org/petition. And very much appreciate folks supporting that. I'm from the local section and done a bunch of IEEE activities, and I'd like to get a chance to do that. Thank you very much.
And once again, Basal, Joyce, this was amazing.